Hello guys, I'm back, at least for a few videos. The kids are taking a break and are on vacation for a few more days, and so there's not much work going on their apartment remodel, so I'm not working there. I thought I would kind of talk a little bit about, I've gotten questions about this before, about two different circuits in a radio. This has been our nice little schematic that we've been following. But the 6K8, and it could be a 6A7, it can be a 6S7, it can be any number of different tubes. But what is known as the mixer, oscillator, detector, first detector tube, converter tube, but how does it actually operate? What is going on inside, and how does it take two different frequencies, our local oscillator and our incoming signal, and do something with them to give us a frequency that we need for our IFs, in this case 455 kilocycles. And the other one I want to talk about is what is also is the detector tube, or also known, and sometimes you'll see on a schematic, as the second detector, and the mixer is your first detector. So let's take a little look at that. Now, excuse the drawing, it is not anywhere near scale, it's not anywhere near perfect, it's not anywhere near. I'm just hoping that I can kind of give you a general idea, and enough to be able to kind of explain what does happen in a simple way, and so that you can kind of see it. So I've never admitted or claimed to be any type of artist, and without graph paper I'm a long ways from it. So with that said, let's take a look at what's going on. The red we will consider our signal, so the radio station coming in, and I should have probably used a different color for the other one, but it's red, and one's orange and one's red. So this one right here, coming down through and up, and where I've got this TS that just is standing for the period of the wave from one peak to the other, is our signal coming in. Now, it's not drawn to any type of scale. The blue that you see going through here is our oscillator, and then the orange is one of what we end up with. Now, there's several frequencies we actually end up with. This one will happen to be the subtraction. You can actually add the frequencies together as well, and you'll get that. But the T sub R just stands for the resultant frequency. Now, how does it get that? Well, when you get two peaks, like right here, they're on the same side as your zero line. They're both going positive at the same time, or roughly the same time. Those will add together. They're in phase, and when they're in phase, you end up with in this case our positive, we end up with a combined amplitude frequency peak. When those two peaks are negative to each other, 180 degrees out of phase, such as right here and right here, and this orange colored line should be more closer about in this point here, that's when it will actually zero out. Making the assumption that these are pretty much the same level, and they generally are in the tube. They're close, they're off by a little bit, but not a lot in level. So When they're opposite, they subtract. When they're on the same side, or pretty much in phase or close to in phase, they add. Since they're two different frequencies, at certain times they're adding and at other times they're subtracting. As you can see here, these are a lot closer together, so they're at certain points, like right here we're adding, here we're adding, here we're adding, here we're adding, here we're adding. But everywhere else, pretty much we are subtracting, so we end up with the resultant frequency that will actually be quite a bit wider band, and it should be. Like I said, this is not drawn to scale. The red should be a lot closer in. This should be a lot longer. And that's basically how it does it. It's just the fact that even though you got two different frequencies, at certain points they do add, and at some points they do subtract. Add, subtracting here, adding here, subtracting here, and adding. And that creates another frequency entirely that's coming out. Now realize what's coming out of that tube is this, your local oscillator frequency that has not been bothered at all will come out of the tube. Your signal will come out of the tube, not being bothered, nothing been added or subtracted from it. One resultant, which is the subtraction of them, and I didn't draw in the resultant. You can actually draw one in where they actually add together. There's other points that you can actually work in here where you can actually get the two frequencies to add together. So those are the four primary frequencies, plus several harmonics that will come out of it. But that's basically all it's doing. When they are in phase or pretty close in phase, they do add. When they're out of phase, such as here, they start subtracting, and the resultant, when they're subtracting, will start heading towards zero and go across zero line at that point. When they're adding, when they're in phase and they're adding, they just create a resultant with a higher amplitude. And that's all there is to it. That's how it works. Now the IF can is the guy that's going to figure out what to let through and what not to, and it's set at 455, so it's going to only allow 455 kilocycle signal to get through. It'll stop everything else. So I hope that kind of answers some questions on that. Now we'll try to look at what the other one's doing in a very simple way. Erase this and see if I can halfway draw it. So, draw a nice long centering line here, our 0 point. Let's take red. We'll use red. Is our audio. Use green. Is our RF. Now, what comes into our detector tube, coming right out of here, right out of the output of the second IF, will be this signal. You'll see this. and it'll just continue on. Now, that's all fine and dandy. The only problem with this is I can't do anything with it. The red is the audio portion of this RF that's in there. The green is the 455 kilocycles, and the red will be our audio. The thing is, these are mirrored images of each other. Now, if I was to take this and try to feed it in any type of coil or transformer, run it through the audio amplifier section and out to the audio output transformer and out to the speaker, what would end up happening is these two, since they're 180 degrees out of phase and they're identical and they're mirrored, they would actually go to zero. You would have absolutely nothing. So what the detector actually does is this. That's it. That's all it does. Cuts off half of it. That's why it's just a diode. It's just a diode. It's just a rectifier. The same thing happens in your rectifier, such as the 5X4 here. Same thing happens here, the AC. When I send an AC signal in there, it hits that diode, one of them diodes in there, it cuts off part of that AC signal, either the top or the bottom half. But it cuts it off, only leaving one hump. Since it's a full wave rectifier, which is what this is, then you'll just end up with several little humps. Just kind of like this, with nothing in the middle here. Just several humps. Well, the detector tube is nothing but a diode. And that's all it's doing. We're using one single diode, and we're just cutting one half off, and that's it. Now, this is all fine and dandy. I can amplify this now and everything, but I got this noise in here. I got to get rid of the noise. This 455 is going to cause all kinds of headaches and harmonics and problems and heat and everything in these output tubes, and it create noise and distortions, and I've got to get rid of it. I don't want that in there. So how do I get rid of it? Well, the simplest way of doing that is filter it. And this one basically, this 0.0001 capacitor right here and the 47K resistor here is a filter. That's all it is. It's a simple filter, RC filter that's in there. Now, some of them will have a tank circuit type where you have a capacitor, resistor, and another capacitor. Some just a single capacitor and resistor. And basically all that filter is doing is, if I look at it in real close, if we would take this and bring it in real large, then what we would see is something like this. We'd have a big swoop of this, and then we would have our signal in here. And what ends up actually happening is, just like any other filter, it charges up a capacitor, and then it brings it down, and then brings it up, then down, and up, it recharges, and then it drains off, and up, and drains off, and it just keeps doing that. Now, depending on how good the filter is, will depend on how much what is known as ripple that's in here. But you end up with a signal that will have a little ripple in it coming out, and I've gotten rid of this here because this is what's charging the cap up, and I end up with just this little ripple. Now, that's fine, but there's a little bit of noise in it. How do I get rid of that? I need to filter it again. And the way I do that is we go ahead and run it through our first audio circuit, just the way it is. And then, coming out of that plate, our signal, we run it through a cap. And this is ground right here on the cathode. This black shows ground, goes down to ground here. At this point, 0.00025 microfarad cap right there is my last little filter. It's a decoupling cap. What it does is it will not let this audio through. But this little bit of ripple, it's higher frequency. It's still feeding at them frequencies of that 455. That ripple will easily pass through that 250 picofarad cap. But the audio, it sees it as a roadblock. It will not go through it. So it doesn't like going through that. So then you end up with leftover is a beautiful audio signal coming out. And then all we got to do with that is we actually run a center line through there, and we can feed it right into our audio amplifier, and at that point we have an output that we can send to the transformer and then onto the speaker. But that's all it basically does, and it's the same thing that actually happens with a power supply, except different frequencies. Power supply is dealing with 60 cycles, where a 4-wave is 120 cycles. But it's the same thing. Runs it through a pi filter, which in this case is actually using the speaker field as part of the pi. So you have a cap, filled, cap, just like you've seen in any other power supplies, a lot of power supplies. Some of them you'll have a cap and a resistor and a cap. But it does the same thing. It's doing this, and as you continue filtering it, you get it smoother and smoother, and you get it hopefully with this field winding, which is nothing but a choke, which hates AC, blocks it like crazy. And the two filter caps will actually bring it real smooth so there's no ripple. And then you feed it on out as a DC signal. In this case, we're looking for one AC signal, but we want to filter out the other AC signal, but we use the same technique. We throw a diode in, or rectifier, and then we run it through a filter. And after we're done with the all full complete filtering and everything, what we end up with is a nice smooth wave, audio frequency wave, that now we can amplify and for your listening pleasure. So I hope you kind of understand that. It really is not complicated. It's actually pretty simple in how it works. But the two, whether you're looking at a power supply or you're looking at the actual detector, they're actually the same thing, just that they work with different frequencies. And the resultant that they end up with is a little different. So I hope that does help out and answer some questions. If there is any more questions on it or anything, we can go a little more in depth into it and in our understanding of it. So I guess that's about all I've got for right now. We'll probably work on looking through more of the schematic on the next video. Should be coming up maybe like tomorrow on something. Kind of get a little more feel of it, the flow. Mainly we're just looking at the flow, how things flow through and what each component's doing in there and why it's there. So until next time, I want to thank you very much for watching, and I want to thank all my new subscribers. I want to thank all my old subscribers who's sticking around. It's been a long time, and sorry that it has, and sorry that I've let you down kind of a bit. But I'll try to get some videos out, and you know, time permitting, and kind of get you caught up before we hopefully go back to work. By the end of summer, though, things will get back to normal. So thanks again for watching. I'll see you on the next video. You all have a good day.